For today's lesson, we are going to be learning how to graph transformations of cosecant and secant functions. Down here, we have an example of a cosecant and secant function. They look a little bit confusing, but you will find that through the help of the sine and cosine function, these are actually very easy to graph. Let's go ahead and start off with our first function, the cosecant function. In order to graph this, we're going to start with our sine function. Here's a table of values, and here's our sine function. You'll notice that at 0, the sine function has a value of 0. And you can picture this on your unit circle. At pi over 2, or 90 degrees, the sine function has a value of 1. And I've listed these in our table. If we think about our cosecant function, however, this is the reciprocal of the sine function. So if we take 0 over 1 and we take the reciprocal, we end up with 1 over 0, which is undefined. How does that look in our graph? Well, at 0, since we have an undefined value, we would need to put in an asymptote here. In fact, everywhere where we have a 0, such as here, and down here at 2 pi, since these are all undefined, we would want to go ahead and sketch in an asymptote. Notice how I'm using the graph of the sine function to help me graph the cosecant function. What's next? Let's look at pi over 2. This has a value of 1. The reciprocal of 1 is still just 1. The reciprocal of negative 1 over here at 3 pi over 2 is still negative 1. So I know that I'm going to have a point here on my cosecant graph as well as here. Right now, that might not be enough to help you sketch this graph. Let's look at an additional point. How about here at positive 1/2 and down here at negative 1/2? If we take the reciprocal of 1/2, we get 2. So instead of having a value here, we would have a value maybe right here. And then over here, where the graph hits 1/2, the reciprocal would still be 2, so we'll have a value here and here. If we are to connect these dots, we can see then that this cosecant graph forms a sort of parabola, and the end behavior is going to follow these asymptotes. Let's look at this one. If we go to 1/2, which is right here, the reciprocal of negative 1/2 is negative 2. And the same thing over here. Now you can see the shape of this cosecant graph, and this looks very similar to what you saw on the first page. Do you see how we use the cosecant function to help us graph, or the sine function, I should say, to help us graph the cosecant function? But what happens when we have transformations? This is also very simple to graph. All we need to do is graph this in its sine form. Since you already know how to graph transformations to the sine and cosine function, if we can graph this transformed sine function, we can easily graph the cosecant function. So the first thing is to identify our amplitude, our period, any phase shifts, or vertical or horizontal shifts. Looking at our amplitude, we can see that it's 2. Our period, well, our period is always 2 pi, but now we're saying that we're going to have 2 cycles within 2 pi. So we divide 2 pi by 2 and get pi. From this, we can identify each of our quarters on our unit circle by multiplying by a quarter or dividing by 4. So we know we're going to have a quarter every pi over 4. Our midline is a result of this shift. We have a vertical shift up of 3. That changes our midline from down here at 0 to a value of 3. So we would just need to take our midline and move it up to 3. Knowing that we have an amplitude of 2, then from our midline we would go up 2, which would put us at 5, and we would drop down 2, which would put it at 1. Since our quarters happen every pi over 4, and we don't have any phase shifts or horizontal shifts, we would start here at 0. Our first point would be at pi over 4. Our second point would be at 2 pi over 4. or pi over 2 reduced, then 3 pi over 4, and finally pi. And as we said, we complete one full rotation every pi. Now let's graph our sine function. I've just sketched in the sine function since this really isn't what we're looking for. We're looking for the cosecant of the same transformations. But now that I've sketched in my sine function, I can go ahead and draw in my asymptotes, which we know will be anywhere where we have a value of 0. Since we have a new midline, our value of 0 happens up here at 3. Now that I have my asymptotes in, I know that the base or the vertex of these parabolas happens at the maximum and at the minimum of my sine curves. So all I really need is that one point, and I know that the end behavior will follow these asymptotes. So from these amplitudes, I can then sketch in my cosecant graph. Let's try one with the sine or with a cosine, and let's sketch a secant graph. Here's a typical cosine graph. Let's look at our key points. When we have a value of 0, we know that cosine is 1. The reciprocal of that is still 1. Obviously, anywhere we have 0, we're going to end up with an undefined value. The reciprocal of negative 1 over 1 is still 1 over negative 1, so that's negative 1. And then we have undefined, and then we have 1. Graphing these, once again, we know that anywhere where we see a value of 0, here, 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 and here, we would need to draw in some asymptotes. The behavior of the secant graph works the same as the cosecant graph. It looks the same. So remember, when we have 1, and the reciprocal is 1, we're going to have a point here, and the end behavior will follow these asymptotes. Same thing with our amplitude down here at negative 1. Well, the reciprocal of that is still negative 1, so we would come down here and draw in our parabola of sorts. Now this is showing more than one period, but you could continue on at every amplitude. You know that this is going to repeat in each section. And that is how you sketch a secant graph. Let's try one with transformations. If you like, pause the video and see if you can sketch this graph. Well, in order to sketch the secant, we need to first sketch the cosine. So, let's look at what we have. We have 4x plus pi. We need to determine the period, so we need to factor out that 4. When we do that, we get 4 times x plus pi divided by 4 would then be pi over 4. Now we're ready to determine our amplitude, period, phase shift, vertical shifts, whatever we might have. Let's first look at our amplitude. There is no change, it's 1. Now we have a period of 4. Or I should say 4 cycles in 2 pi. So we take our 2 pi and divide by 4 to determine that that actually is pi over 2. Now we need to figure out our quarters. If we multiply that by 1/4, we know that we have a quarter then every pi over 8. The other thing we have is a phase shift. In other words, a horizontal shift. Since this is x plus pi over 2, if we set it equal to 0 and solve for x, we actually get a phase shift of negative pi over 4. So we know that our first point here will be at negative pi over 4. Now it's time to mark each of our quarters. So we're going to add pi over 8 to negative pi over 4. When we add pi over 8, we get negative pi over 8. So our next point would be here at negative pi over 8. If we add a pi over 8 to that, we get 0. And another one, we get positive pi over 8. We'll need one more mark to make 4 quarters, so 1 pi over 8 plus pi over 8 is 2 pi over 8, or pi over 4. From here, we're ready to sketch our cosine curve. Now that we have one full period sketched in for our cosine curve, I'm ready to draw in my asymptotes. I don't need a table because I know that anywhere where I have a value of 0, I will have a vertical asymptote, as this will be undefined when I take the reciprocal. From here, I can take the high, which is up here, and sketch part of my parabola in accordance with the asymptotes. And here, and then down below here, I can sketch another one. And now I have sketched my secant curve with these transformations. That concludes our lesson today on how to transform the cosecant and secant functions. So if you remember, if you continue to graph the sine and the cosine as you normally would using the transformations, it's easy to sketch in the asymptotes and the cosecant and secant curves.